What if, somewhere between the orbits of Mars and Jupiter, a silent traveler has just brushed past our sun, a relic older than the solar system itself? Imagine that, a fragment of another star's nursery, gliding through the cosmic dark, untouched for billions of years, now caught in the eye of a camera orbiting Mars. You see, that's exactly what happened when China's Mars orbiter captured the closest ever image of 3I Atlas, an interstellar visitor that seems to defy what we thought we knew. It lost more than 13% of its mass as it swung past the sun, and yet no tail, no glittering plume of gas or dust streaming behind it like every comet we've ever seen. Why? What could strip away so much material and still leave nothing visible in its wake? Perhaps the laws we use to describe these celestial wanderers are missing a small but crucial note, a whisper of physics we've not yet heard. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. It began as a routine calibration. The Tianwen-1 orbiter, long past the prime phase of its Mars mission, was quietly circling the red planet, its cameras mostly asleep, its instruments resting after years of service. Yet somewhere in the control rooms back on Earth, a handful of engineers and scientists saw an opportunity. They wondered what if the old spacecraft could be used again, not to look at Mars, but at something far more elusive, something fleeting. You see, spacecraft age like living things. Their sensors drift, their trajectories become less precise. But every now and then, there's a chance to breathe new life into them, to let them glimpse something never seen before. So, they tried. They recalculated orbital paths, turned old software into new instruments, and pointed Tianwen, one toward an object moving through the darkness at impossible speed. 3I Atlas, a visitor from another star. Imagine that a tiny rock, perhaps only a few hundred meters across, crossing the solar system, gliding between planets that have never known its kind. From the ground, telescopes could barely follow it. It was too faint, too fast. But the Mars orbiter, being closer to its path, could take a shot. Not a perfect one, no. That would be asking too much, but one that might reveal a little more about what this interstellar traveler truly was. The maneuver itself was a marvel. Locking onto a target so small, so dim, and moving so quickly that even a blink could lose it, required precision beyond the design of Tianwen-1. Its sensors weren't meant to track such things. Its guidance algorithms had to be reprogrammed, its camera exposure recalibrated for light weaker than any Martian reflection. Think of it as trying to photograph a single firefly from thousands of kilometers away, while you yourself are spinning through the void. Every slight vibration mattered. Every calculation had to be perfect, and somehow, against those odds, they did it. When the image came through, grainy, faint, but clear enough, it sent a ripple through the scientific community. The object appeared not as a streak, but as a steady point, reflecting sunlight with an odd, muted glow. That was unexpected. Normally, a comet passing so near to the sun would show a flamboyant tail, a stream of gas and dust driven outward by solar radiation. But 3I Atlas showed nothing of the sort. Just a body, dark and cold, shedding mass invisibly. It was, in every sense, alien. And that's the thing. Moments like this remind us how much of science is about curiosity, not certainty. The team behind Tianwen-1 didn't just capture an image. They rekindled a way of thinking. They turned an old machine into an explorer again. The orbiter's lenses, meant to map craters and canyons, were now peering across interstellar space, reaching towards something untouched by any human hand. In a way, that single photograph was an act of defiance, a quiet rebellion against the limits of our expectations. You might wonder why this event mattered so much. After all, a few pixels of light hardly seem like a revolution. But context matters. You see, this was only the third confirmed interstellar object ever observed by humanity. The first was one Oumuamua, discovered in 2017, whose strange cigar-like shape and mysterious acceleration sparked endless debate. The second was 2I Borisov, a more traditional comet with a visible tail. And now, 3i Atlas, both familiar and strange, fitting neither category neatly. Each one, like a single syllable from a cosmic language we're only beginning to learn, adds something to the story. From Tianwen-1's perspective, the view was unlike any other. The sun was a distant glare, Mars a quiet spectator, and beyond, 3i Atlas drifted through the blackness, a messenger from another epoch. The engineers adjusted exposure after exposure, waiting for the perfect alignment. There must have been moments of silence in the control room, moments where time seemed to stop, only the faint hum of equipment and the whisper of calculations. Then, a signal, data received. The image was there, not grand, not cinematic, but extraordinary in its existence. When the first scientists saw it, they were struck by the starkness of it all. There was no fiery plume, no outburst, no cometary drama. The object was bare, almost stoic, its surface reflecting light unevenly, hinting at metallic patches or strange mineral compositions. Some described it as dull grey, others as faintly blue, though colour in such low light can deceive. What they could agree on, however, was that the object was losing mass over 13% as it grazed the sun, and yet, somehow, that loss left no trace visible to the eye. That raised a new question, one that would echo through observatories for months. Where did the tail go? Perhaps the surface was sealed, covered in refractory materials that refused to sublimate. Perhaps the loss was internal, gases escaping through microfractures, too thin to reflect sunlight. Or perhaps the dust grains were so large they fell back, forming no tail at all. The truth, at least for now, remains hidden. But in that uncertainty lies the beauty of it. Science thrives not on answers, but on better questions. And Tianwen-1, once a silent orbiter, had just given us one of the best in recent memory. There's something deeply poetic about a spacecraft designed to study Mars, turning its gaze outward toward the unknown. It's like an old explorer, weary but still curious, glancing up from the map of familiar lands to wonder what lies beyond the horizon. And, in that sense, Tianwen-1 became a symbol not of technology alone, but of persistence, of the human impulse to look again, to reuse, to repurpose, to ask one more question. The technical feat itself was staggering. The spacecraft had to compensate for both its own orbital motion and the velocity of 3i Atlas, which was traveling tens of kilometers per second relative to Mars. Light travel time delays made communication tricky. Commands sent from Earth arrived minutes later, long after each exposure had been taken. That meant every shot had to be pre-programmed, every motion predicted. There were no second chances. The result depended on trust in mathematics, in code, in the precision of human foresight. And yet, the image arrived, crisp enough to analyze. Spectroscopic readings suggested a mix of elements, though incomplete. The object's albedo, its reflectivity, was unusually low. That hinted at a surface rich in carbon compounds, perhaps baked and weathered by cosmic radiation during its eons-long journey through interstellar space. It was ancient beyond reckoning, older than the solar system, older than the Earth itself. It had watched stars be born and die, passed through molecular clouds, drifted for billions of years, before finally falling into our tiny patch of the galaxy. And for a few brief moments, a camera orbiting Mars saw it. That's when something shifted in the tone of the discussion. What began as a technical triumph became a philosophical moment. If something so small, so insignificant, could carry with it the memory of distant stars, then perhaps everything we touch, every atom around us, has done the same. We are, in a very real sense, surrounded by travelers from other worlds, even if most are invisible. The dust in your breath, the iron in your blood, they too once drifted through space before finding their place in you. You see, when scientists talk about interstellar objects, they aren't just cataloguing curiosities. They're reading the universe's autobiography, written in stone and ice. Each one tells us where it came from, what kind of star birthed it, what kind of chemistry shaped it. And by extension, it tells us something about ourselves, how we fit into this web of cosmic history. For China's space program, this success was more than just a line in a report. It showed that even after a mission's official objectives end, exploration doesn't have to. The reuse of Tianwen-1's instruments reflected a spirit of scientific adaptability that goes beyond nations or politics. It's the same impulse that once drove Galileo to turn his telescope to Jupiter, or the Voyager probes to keep sending whispers from the edge of the sun's influence. The images were later cross-referenced with those from observatories on Earth, allowing scientists to triangulate 3I Atlas's precise path. The data matched beautifully, confirming that the orbiter had indeed captured the object as it passed through the inner solar system. The excitement was palpable. New measurements suggested that the object's density might be lower than rock, but higher than ice, something in between, a hybrid of materials. And that made sense, perhaps, for something formed in another planetary nursery, under another sun's warmth. As the days went by, the team continued to refine their models. They simulated different angles, tried to estimate the rotation rate of 3I Atlas, its surface roughness, its thermal inertia. The numbers hinted at a body that absorbed sunlight unevenly, perhaps tumbling chaotically as it moved. And that tumbling might explain why it lost mass without producing a tail material venting irregularly, not in steady jets, but in silent bursts too faint to see. Still, none of it was definitive, and that's what made it beautiful. Every explanation opened another question, every measurement carried uncertainty. The scientists found themselves at that familiar boundary between knowledge and mystery, where data ends and imagination begins. It's there, in that quiet gap, that science feels most alive. Late one evening, as the Mars orbiter continued its path around the red planet, an engineer reportedly looked at the final set of images and said softly, "It's strange to think this might be the last photo we ever take of something that came from another star." The room fell silent, the monitors glowed. Outside, Mars spun beneath, unknowing. And somewhere out there, 3I Atlas drifted on, leaving behind only its image and its questions. The story of Tianwen-1's photograph isn't just about a spacecraft or a comet. It's about perspective, about what happens when we look at the familiar with new eyes. A mission designed for one world ended up touching another kind of frontier entirely. It showed that even in the twilight of a machine's life, there's room for discovery. Perhaps that's true of us too. And as the data settled and the headlines faded, one question remained. What exactly happened to that missing tail? Why did a body that lost so much mass show so little evidence of it? That, you see, leads us deeper into the heart of physics itself, into the strange, invisible processes that govern matter and energy when they meet the sun's relentless heat. And that is where our story drifts next. And so, we come to the mystery itself, the silent evaporation, the invisible shedding, the missing tail. In the language of physics, what happened to 3I Atlas defies the pattern we've come to expect from anything that ventures near the Sunday. When a comet approaches that close, it should sing. Ice should sublimate, jets should roar invisibly through vacuum, and sunlight should scatter through the dust, painting that long luminous veil we call a tail. Yet here was an object that lost 13% of its body mass without a whisper, without a shimmer, without even the faintest trail. It was like watching someone exhale into nothingness. To understand why, we must step back, not just into space, but into the mechanics of matter itself. Comets, as we know them, are made of volatile compounds, water, carbon dioxide, ammonia, frozen solid in the deep cold of interstellar space. As they draw closer to the sun, solar radiation warms their surfaces, and those ices vaporize, carrying dust and gas outward. That is outgassing the breath of a comet. It's what gives them their brightness, their tails, their character. But for 3I Atlas, that expected breath was absent. Something else was happening beneath its surface. Perhaps the best way to picture it is to imagine a dry riverbed. Beneath the crust lies ice, but covered by a layer of dust so thick that heat cannot penetrate. The sun's rays strike, but the warmth stops just shy of the frozen interior. The ice, trapped below, melts slowly, seeping into cracks rather than escaping into space. The mass is lost, yes, but silently, invisibly. Could that be the story here? The team modeling 3I Atlas thought so, at least at first. They simulated how the heat would spread through a body, spinning through sunlight, with patches of darker rock and lighter ice. Their models showed that if the outer shell were carbon-rich or metallic, it might absorb radiation unevenly, creating pockets of warmth that caused localized evaporation. The escaping gases, trapped beneath that dense crust, could vent sporadically small, internal eruptions that eject mass without forming a visible plume. It was elegant, plausible, but incomplete. Because if that were the case, some sign of asymmetry, some flicker of reflected light, should have been seen. None was. That's where the idea of non-volatile loss came in. Some researchers proposed that the mass loss wasn't due to evaporation at all, but to fragmentation, tiny particles breaking away and dispersing in a way too diffuse to catch sunlight. Think of it as a body quietly crumbling, its pieces scattering into dust, too coarse to shine. Such dust would remain gravitationally bound for a while, forming a faint, invisible envelope. It would look, from afar, as if the object simply shrank. Yet even this left questions. How could fragmentation account for the scale of loss without disrupting the object's rotation? How could the disintegration be so uniform, so smooth, that the light curve, the brightness over time, showed almost no irregularity? That was the puzzle. Every answer led to another corridor of mystery. One evening, in a quiet lab, someone ran the thermal models again, this time assuming the surface was coated with a layer of nickel and iron compounds, dense, refractory materials that barely respond to solar heat. That tiny change shifted the outcome dramatically. Instead of a comet boiling away, the model predicted a body that would absorb heat on its surface and re-radiate it quickly, allowing almost no penetration into its interior. The only way to lose mass in that scenario would be through microscopic, sputtering atoms knocked free by the sun's energetic particles. Individually, such atoms would be invisible, but over time, they could add up. And there it was, a mechanism capable of eroding 13% of the body without leaving a visible trace. You see, sputtering isn't something we often think about in the context of comets. It's a process more commonly associated with spacecraft when solar wind slowly strips material from exposed metal. But 3I Atlas wasn't like any comet we've known. If it had spent eons traveling between stars, its surface would have been bombarded by cosmic rays, hardened by radiation into something closer to stone than ice. The gentle, persistent sculpting by the interstellar medium would have changed it, fusing volatile materials into more stable compounds. By the time it arrived in our system, perhaps it was no longer a comet in the traditional sense, but a relic of transformation, a fossilized traveler. And that's the thing, when something travels between stars, time does strange things to it. At interstellar speeds, collisions with even tiny dust grains can alter its surface chemistry. Layers form, layers erode, and what once was icy becomes metallic. What once reflected light becomes darkened. The object might still carry traces of its original composition deep within, but the skin we see is an armor forged by time and radiation. That armor could explain everything: the lack of tail, the muted glow, the quiet shedding of mass. Still, not everyone agreed. Some astronomers pointed to the energy balance. If sputtering alone accounted for the mass loss, then the object's temperature must have risen more than observations suggested. Others argued for an even stranger idea, that the mass loss was not entirely physical but partly optical. Perhaps the brightening and dimming we interpreted as material loss were actually caused by rotation and shadowing effects, the play of light on an oddly shaped body. That possibility had haunted the case of one Oumuamua, whose acceleration without a visible tail had sparked years of debate. Could 3I Atlas be repeating that enigma, a second act in the same cosmic play? There's a quiet excitement in these discussions, an almost childlike wonder disguised as scientific rigor. Because, well, what we're really asking is whether we've met another kind of object altogether, a category that doesn't fit the neat boundaries of comet or asteroid, something new, something that belongs to the in-between. To test these hypotheses, the researchers compared 3I Atlas's brightness profile with standard comet models. They calculated what its tail should have looked like if the mass loss were purely from volatile sublimation. The results were clear. A typical comet, losing that much mass, should have shown a tail at least thousands of kilometers long, easily visible, even with modest telescopes. The absence of that tail meant the expelled material had to be either too dark, too coarse, or too slow to escape. None of those options fit perfectly. Some even proposed that magnetic interactions could play a role. As the solar wind flowed past the object, it could have generated electromagnetic forces that deflected charged particles, shaping the outflow into forms we could not easily detect from our vantage point. It sounds speculative, perhaps even fanciful, but space is full of such invisible architectures, fields, and forces that sculpt dust and plasma into patterns the eye can't see. What I find most fascinating is that through all these debates, there is a deeper, almost philosophical theme emerging. The laws of physics are not in question, but their expression in this tiny ancient fragment might be more subtle than we've anticipated. We tend to think of nature as predictable, repeatable, orderly. But at the scale of the cosmos, where every grain of dust has a unique history, the boundaries blur. What looks like defiance is often denied, just complexity revealing itself. If we step back and imagine 3I Atlas during its closest approach to the Sun, it becomes almost poetic. The object passes through the halo of solar radiation, buffeted by streams of charged particles, glowing faintly as its atoms are slowly stripped away. No tail flares behind it, no trail of dust glitters in its wake. Only silence, only the patient erosion of a traveler too old to shine. It's as if the universe itself was whispering a secret, and we caught just enough of it to know we'd missed the rest. And then there's the matter of probability. Losing 13% of mass without visual evidence isn't just rare, it borders on the improbable. To understand it, scientists turn to statistics, simulating thousands of interstellar bodies with varying compositions and thermal properties. Only a handful behaved like 3I Atlas, and even those required unusual initial conditions, dense crusts, low spin rates, ancient surfaces compacted by radiation. The odds of encountering such an object in our brief window of astronomical observation are astronomically low, yet here it was. It reminds us that rarity doesn't mean impossibility. It just means we've been lucky, or perhaps chosen by chance to witness something delicate. Well, perhaps that's the beauty of it. The equations that govern heat transfer, sublimation, and radiation are universal, but their outcomes depend on context. The same physics that shapes a comet's tail might erase another's, depending on how time and distance have sculpted it. The cosmos doesn't repeat itself exactly, it improvises. In that sense, 3I Atlas is a performer in a grander symphony, playing a note slightly off-key, reminding us that even in the precision of mathematics, there is room for mystery. Its silent evaporation may not be a violation of law, but an expansion of understanding. It shows that space, in its vastness, can still surprise us with subtlety rather than spectacle. Somewhere, in a university lab, a graduate student might be running a new simulation right now, tweaking variables, wondering if perhaps the object's spin axis was tilted just so, or its internal structure layered like an onion, creating resonant heating cycles that led to controlled, invisible loss. Every adjustment brings the model closer, but never perfectly. And that's the essence of scientific pursuit, it's never finished. Each model is a conversation with the unknown. You know, when I think about that, I'm reminded that this isn't just about rocks and radiation. It's about humility. It's about standing at the edge of what we know and realizing that the universe still holds its cards close. The missing tail of 3I Atlas isn't a failure of prediction, it's an invitation. And that invitation leads us onward, because beneath the physical mechanisms, beneath the sputtering and fragmentation and magnetic fields, lies a deeper question still. What was this object made of? What secrets were written in its chemistry, in the ratio of elements on its surface, in the whisper of light it reflected? To understand that, we must look closer, beyond physics, into the language of matter itself. And so, our story turns toward the composition of this ancient traveler, toward the strange abundance of nickel, the scarcity of water, and the chemical clues that point to a birthplace far from any sun we've ever known. In the weeks that followed, observatories across Earth turned their instruments toward the fading trace of 3I Atlas, hoping to find the missing tail that physics demanded should exist. Telescopes in Chile, Hawaii, and the Canary Islands each captured sequences of images, stacking exposures, subtracting the glare of nearby stars, and stretching the faintest signals to their limits. Yet, each dataset told the same story. Nothing. The space around the interstellar visitor was dark, clean, unadorned by the filament of dust or the wispy arc of gas that defines a comet's passing. It was, as one astronomer said quietly, a disappearance, not a display. You see, it's strange how the absence of something can feel heavier than its presence. The team began to re-examine every piece of data gathered near perihelion, the moment when 3I Atlas was closest to the Sunday. At that distance, heat should have been merciless. The surface temperature could easily have risen above the point where ice sublimates explosively. Even refractory materials, metals like nickel and iron, begin to change their crystalline structure under such extremes. By all conventional reasoning, something visible should have emerged. Yet, when they overlaid the orbital models and compared images from different observatories, the silence of space persisted. At first, some suspected geometry might be the culprit. Maybe the tail existed, but we were simply looking along its axis, seeing it edge on, reduced to a line too thin to register. But geometry has fingerprints, polarization effects, faint halos, asymmetries in brightness. When scientists checked these clues, the verdict was clear: no such signals were present. The object truly lacked a tail, no matter where it was viewed from. Others wondered whether instrumental noise could be hiding it. After all, the glare of the sun, even when filtered, can create faint streaks that mimic or erase delicate patterns of light. Teams ran simulations of their detectors, injecting artificial tails into real images to test whether they would have been seen. The result was sobering. Even a minimal tail less than 1%, the brightness of a typical comet, would have been detected. Yet 3I Atlas showed none. So the question deepened: where did the missing material go? If 13% of the object's mass had been lost, as thermal models insisted, it had to exist somewhere. Matter, after all, doesn't vanish. It transforms, disperses, hides, but it does not cease. Some began to suspect the lost mass was not in the form of dust or vapor at all, but in neutral atoms dispersed into the solar wind, indistinguishable from the stream of charged particles constantly flowing outward from the Sunday. If so, the comet's material might have been absorbed seamlessly into the solar environment, dissolving into invisibility. To explore that possibility, researchers examined data from the Solar and Heliospheric Observatory, looking for any trace of altered plasma near the comet's path. Nothing obvious appeared, but that, too, was a kind of clue. It suggested the material released was not energetic, not ionized, but quiet, perhaps larger grains, perhaps bound molecular clusters too massive to interact strongly with solar fields. There's a poetic irony in that. The comet shed part of itself into the wind, yet left no scar, no glow, no evidence that it had ever been here. It was as if it had whispered into the sun and vanished. Well, the human mind doesn't rest easily with such silence. Patterns demand explanation. Scientists began to categorize the possibilities. Either the lost mass was hidden by geometry, absorbed by the solar environment, or composed of something so unusual that it interacted with light in ways we don't yet understand. None of these ideas fit comfortably, but they each carried a kernel of plausibility. One late night in an observatory in northern Chile, a young astronomer stared at the composite image and muttered, "Maybe the tail didn't disappear. Maybe it never formed at all." That thought lingered in the air like static. What if the internal processes of 3I Atlas were fundamentally different from those of comets born in our solar system? What if its chemistry, forged under another star's light, didn't respond to heat the way we expect? To test that, teams compared 3I Atlas with data from both 1I Oumuamua and 2I Borisov, the only other known interstellar visitors. Borisov behaved like a textbook. Comet, it had a glorious tail, strong outgassing, bright jets. Oumuamua, on the other hand, displayed acceleration without visible emission, its tail seemingly absent too. And now, a third object had arrived, echoing Oumuamua's silence. A pattern was forming, subtle but undeniable. Perhaps the first two interstellar bodies weren't anomalies after all. Perhaps this was the rule, not the exception. If that were true, it would mean that objects born beyond our solar system carry within them a kind of austerity, a chemistry lean in volatiles, rich in metals and dust, hardened by radiation and time. They might not sprout tails because they have nothing left to lose. Instead of soft, porous comets, they are stone relics, the burnt cores of worlds that never formed. It's a haunting thought that every interstellar visitor we meet could be a fragment of a failed planet, the bones of creation drifting endlessly between stars. And yet, even that didn't explain everything. Because you see, 3I Atlas didn't just lack a tail, it also failed to brighten as much as predicted. As it approached the sun, it should have grown more reflective, its surface releasing fine dust that scatters light. But its luminosity curve was flat, indifferent, almost bored by the sun's presence. That meant the surface was not only dark but also unusually cohesive. Some likened it to meteorite crusts, others to basaltic rock. Still, the precise mechanism of its invisible evaporation remained elusive. When the spectroscopic readings came in from a ground-based infrared observatory, they added another layer to the puzzle. The reflected spectrum showed faint but distinct absorption lines corresponding to silicates and metal oxides, yet the usual water signature, a broad dip near 3 microns, was absent. There was no trace of hydrated minerals, no evidence of frozen volatiles. This wasn't a comet losing water. It was a dry, dense object, shedding something else entirely. Perhaps gases trapped in microscopic cavities, or volatile metals released in molecular clusters. A researcher from the European Southern Observatory proposed a model of transient microdust particles, large enough to avoid scattering light effectively, yet small enough to escape gravitational binding. If such grains were released slowly, they could drift away undetected, contributing to the mass loss without forming a visible structure. But this too depended on assumptions about the object's spin and texture, neither of which could be directly observed. And that's the challenge with mysteries like these. Nature doesn't hand over her variables. She offers fragments, shadows, the patterns of light. The rest is inference, a game of patience and humility. Perhaps, in the end, the missing tail isn't a single phenomenon, but a combination of all these effects: geometry, chemistry, radiation, and coincidence. Perhaps what we call missing is simply our expectation colliding with the universe's indifference. We imagined a bright, flamboyant trail, but 3I Atlas chose subtlety. Its loss was real but invisible, hidden in the wavelengths our eyes can't see. Still, the question lingers: where did the matter go? When scientists mapped the trajectory of the object's orbit and projected the expected dust dispersion, they found something almost poetic. The area where its invisible tail should have extended overlapped with a faint enhancement of interplanetary dust, measured months later, so faint it could barely be confirmed. Was that its trace, or just coincidence? It's impossible to say. But perhaps, in a way, the dust of 3I Atlas is already part of us, blending into the background of our solar system, indistinguishable from the motes that drift between Earth and Mars. You know, that idea has a quiet beauty to it. A traveler from another star enters our system, sheds a part of itself, and disappears, leaving behind particles that may one day fall upon a planet's atmosphere, perhaps even ours. To breathe, then, is to participate in that story, to inhale, unknowingly, a molecule from another sun. And that's the thing about the missing tail. Its absence is not an emptiness, but a kind of transformation. The material didn't vanish. It became something else, something too dispersed, too quiet for us to see. The comet's death, if we can call it that, was graceful, almost spiritual, a dissolution into the larger flow of cosmic matter. As the months passed, attention turned to the next set of questions. If the tail did not appear because the material itself behaved differently, then what, precisely, was that material? The answer, it seemed, would not lie in light curves or dust models, but in the chemistry of reflection, in the subtle spectral ratios that reveal an object's true nature. And so, scientists began to focus on composition, on the strange abundance of nickel compared to iron, on the near-total absence of water, on the possibility that this object carried within it the signature of a world forged under conditions utterly unlike our own. In that pursuit, they were not just studying a rock. They were peering into another solar system's history, another star's lost planetesimal. The question of the missing tail had not closed the case. It had only deepened it. And as telescopes recalibrated, and data scientists turned to spectrometers and chemical analysis, the focus shifted gently, inevitably, toward the next layer of mystery, the riddle of what 3I Atlas was truly made of and what story its atoms might still be trying to tell. When the spectral data finally arrived, it came not as a grand revelation, but as a whisper, thin lines and subtle dips across a field of light. Yet within those faint signatures lay the truth about 3I Atlas, a truth that turned out to be far stranger than anyone expected. You see, light carries memory. Every reflection, every absorption, encodes the story of the atoms that shaped it. And when scientists began to decode that story, they found a composition unlike anything catalogued in our solar system. The first clue came from the relative strength of certain metallic lines. The nickel signature was unmistakable, strong, confident, standing out like a bell tone in a quiet hall. Iron, by contrast, was subdued, weaker than it should have been if the ratio mirrored that of most planetary bodies. Nickel over iron. It sounds like a small thing, a shift in proportion, but in planetary chemistry, that imbalance speaks volumes. In our own solar system, from meteorites to cores of planets, the abundance of iron far exceeds that of nickel. Iron is the bedrock metal of worlds. Nickel is the rare cousin, present, but always in modest company. So when the spectrum of 3I Atlas showed the reverse, the scientific community paused. This was no ordinary rock. That ratio suggested a world forged under conditions of extreme temperature and pressure, where the lighter metal condensed out and the heavier remained trapped or vaporized. It hinted at a birthplace closer to its parent star than any comet we know, perhaps even within the inner zone of a planetary disk, a region where volatile compounds would have burned away long before they could freeze. If that was true, then 3I Atlas wasn't a frozen wanderer from the cold. It was a fragment of something scorched, metallic, born in fire. The absence of water reinforced that conclusion. Across all the instruments, there was no sign, no telltale dip around the wavelengths where water absorbs infrared light. It wasn't that the signal was weak, it was non-existent. For a comet-like object, that is astonishing. Even 2I Borisov, the most cometary of interstellar visitors, carried the spectral fingerprint of water ice. But 3I Atlas, despite losing a measurable fraction of its mass, released nothing that resembled vapor. It was, in essence, dry. Some suggested it might once have been wet, its ice long gone, its surface baked by cosmic radiation over millions of years between the stars. But the more they looked, the more it became clear that the object's mineral composition itself told a different story. Its spectrum contained traces of olivine and pyroxene minerals common to silicate rocks, but their infrared slopes hinted at a crystalline structure modified by thermal metamorphism. In plain terms, this rock had been heated, melted, and cooled slowly. It had experienced geological processes, perhaps within a larger body before being torn free. That realization changed everything. It meant 3I Atlas was not the product of a cloud of dust and ice, but of a world that might once have orbited a star, possessed a crust, and perhaps even known tectonic motion. Somewhere out there, in a distant system, a planet had been shattered, and this small fragment had set off across the galaxy. What Tianwen-1 and Earth's telescopes had captured was, quite literally, a piece of another planet's story. And that's the thing about chemistry, it's not just numbers on a chart, it's a language. Every element, every ratio, is a word in a cosmic sentence. The high nickel content might point to the core of a differentiated world, a place where metals sank inward and silicates floated upward. Or it might indicate the residue of vaporization, the skeletal remains of matter once part of a molten sea. You see, when a star forms, its protoplanetary disk is a chaotic dance of heat and dust. Closer to the star, metals dominate, farther away, ices. That boundary defines the architecture of a planetary system. For 3I Atlas to be so metal-rich, it must have formed on the inner side of that line far too close for water to survive. But then, how did it leave? How did a dense, inner-system object get flung across interstellar space? Perhaps it was the victim of a gravitational cataclysm, a collision, a near miss with a gas giant, an instability that sent debris outward at escape velocity. Or perhaps its parent star died, shedding its planets into the void. Either way, the chemistry of 3I Atlas carried the fingerprints of violence. Laboratories on Earth began to compare its spectral lines with samples from meteorites, lunar rocks, even fragments of asteroids retrieved by missions like Hayabusa and OSIRIS-REx. None matched. The closest analogues were the metallic meteorites, those rare pieces of planetary cores that occasionally fall to Earth, but even they fell short. The ratios were off, the trace elements too exotic. Some researchers noted unusually strong signals from refractory carbides, compounds that only form under extreme heat. Others detected hints of phosphorus and sulfur locked into nickel matrices, suggesting slow crystallization from molten metal. It was as if this object had been born in a crucible and then preserved for billions of years in the cold dark between the stars. Well, perhaps that's what it was. A survivor of creation, a fossil of fire, a fragment of a planetary dawn that happened elsewhere, under another sky. You know, I find that thought both haunting and beautiful. We've always looked outward to find the new, but sometimes what we find are echoes of the familiar rocks that remind us of our own beginnings. 3I Atlas may have circled a star much like the sun, bathed in light we'll never see again, before being cast away. The nickel and iron in its body once flowed like rivers of molten metal, and now, in the 21st century, they shimmer faintly in the spectrum of a telescope's gaze. The data also revealed something else, a spectral slope that was unusually red. That might sound trivial, but it suggests that the surface of 3I Atlas is covered with complex organic residues, the sort formed when radiation bombards carbon compounds for eons. Such tholins, as they're called, are what give outer solar system bodies their reddish hues. But here, in combination with metal-rich chemistry, they create a strange duality, a body both ancient and processed, metallic yet organic. It's as if it carries the memory of both fire and dust. Some astronomers began to speak, almost poetically, of the burnt core of a world wrapped in cosmic rust. It's not far from the truth. That surface, hardened and reddened, could be the reason no visible tail formed. The radiation-hardened crust might have sealed the interior, preventing any volatile materials from escaping. Beneath that layer, pockets of gas or trapped compounds could still exist, but their release would be slow, silent, invisible. Comparing its spectrum to that of comets in our own system highlighted how radical its differences were. Typical comets display strong emission lines of CN, C2, and OH products of volatile ices reacting to sunlight. 3I Atlas had none. Its reflection spectrum was instead dominated by metal oxides and complex carbon residues. In that sense, it resembled more the surface of an asteroid like Psyche or Vesta than a comet. But even then, the nickel enrichment and lack of silicate hydration set it apart. Perhaps it's not a comet at all, some suggested. Perhaps the designation 3I was misleading. What if interstellar objects are more varied than we think? Some icy, some rocky, some metallic, some something else entirely. What if each is a messenger from a different kind of solar system, shaped by rules that rhyme with ours but don't quite repeat? And that's where the implications grow vast. If 3I Atlas was indeed a fragment of a differentiated body, it tells us that planet formation beyond our Sun follows similar principles: metal cores, silicate mantles, the same basic chemistry, but that outcomes diverge. The diversity of matter among the stars may be far greater than we ever imagined. Each visitor, like this, fleeting and silent, expands our sense of what a world can be. But there was still something missing from the picture. The chemical data explained why the object was dry, why it had no tail, why it reflected light the way it did. But it didn't explain the peculiar way its light was polarized, the subtle twisting of its reflected waves that seemed to defy the expected behavior of ordinary dust or metal. That polarization hinted at a surface texture or composition beyond anything seen before, a new layer of the mystery waiting to unfold. And that, you see, is how science moves from one question to the next, each answer peeling back another layer of wonder. The nickel and iron told us about its birth. The lack of water told us about its journey. But the light itself, the way it danced and bent as it left the surface of this interstellar relic, hinted at a deeper secret still. Perhaps, as we turn to that question, we will find that 3I Atlas not only challenges our understanding of composition, but of how light interacts with matter itself. The next chapter of this story, then, belongs not to chemistry, but to the language of light, to the strange, silent signature of its polarization, and to what that might reveal about the hidden texture of a world born under another star. If chemistry gave us a glimpse of what 3I Atlas was made of, then light specifically, the way it twists, bends, and scatters offered something even more intimate, a whisper about its surface, its texture, its soul. When astronomers talk about polarization, they are really talking about the secret choreography of light waves. Every beam that leaves a star vibrates in all directions, but when it bounces off a surface, dust, rock, ice, those vibrations align, forming a signature pattern. That pattern tells us how smooth or rough the surface is, how the particles are shaped, how they cling together or drift apart. It's a kind of fingerprint, written not in atoms but in the dance of photons. For comets in our solar system, that pattern is well known. As sunlight reflects off their clouds of dust and gas, it becomes polarized in a predictable way. The degree of polarization increases with the angle between the sun, the comet, and the observer, reaching a peak before declining again. It's a graceful, familiar curve, but when light from 3I Atlas was analyzed, that familiar curve was nowhere to be found. Instead, the polarization dipped sharply into the negative, a phenomenon so rare, so deep, that it left even seasoned astronomers blinking in disbelief. Negative polarization means that the light, instead of aligning with the scattering plane, turns slightly perpendicular to it. It's as though the photons, upon touching the surface, changed their rhythm and began to move against the flow. That only happens under very special circumstances, when light interacts with particles that are either extremely fine or structured in a peculiar way. In ordinary comets, a mild negative polarization appears near small phase angles, caused by the interplay of light scattered from the front and back of irregular grains. But the depth of the dip, seen in 3I Atlas, was unprecedented. It wasn't mild, it was profound. You see, the universe doesn't easily produce such deep negative polarization unless the material itself is strange. Perhaps the surface of 3I Atlas was made of ultra-compact grains, fused together like glass, their internal reflections cancelling out certain directions of vibration. Or perhaps the surface was layered, coated with microscopic metallic crystals, nickel and iron, reflecting light in opposition to each other, producing that strange twist in the waveform. The same metals that defined its chemistry might also have sculpted its optical signature. One researcher described it poetically. It's as if the light remembered the violence of its birthplace. And that, I think, is the essence of it. Every photon that touched 3I Atlas carried away a trace of that ancient fire, encoded in a polarization curve that defied every expectation. To make sense of it, astronomers compared the data to known models of light scattering. They simulated clouds of spherical dust, irregular grains, fluffy aggregates, compact crusts. None fit. Even the models that had explained the complex polarization of lunar soil, where fine grains and voids create deep interference, effects could not reproduce the depth observed here. It was as if the surface of 3I Atlas was neither dusty nor smooth, neither icy nor metallic, but something in between, a fused landscape of nanostructures formed under pressure and time. Well, perhaps it was. The long exposure to cosmic radiation during its interstellar journey could have etched the surface into a labyrinth of microscopic cavities and ridges, like frost on glass hardened by cosmic rays. Such a surface would scatter light in unpredictable ways, amplifying certain polarizations while silencing others. Over billions of years, as charged particles chipped away its atoms, the object might have developed an optical skin, a crust of paradoxes, where light behaves like sound echoing in a cave of mirrors. And yet, even that idea doesn't capture the full mystery. Because negative polarization is not only a matter of texture, it's also a matter of composition. The wavelengths at which the effect peaked were more consistent with metallic compounds than silicates or organics. Nickel and iron, once again, seem to dominate, but pure metal surfaces tend to depolarize light completely. They don't produce negative polarization unless mixed with dielectric materials. That suggested a hybrid composition, a mosaic of metal grains embedded in a matrix of something darker, more insulating, perhaps carbon. Imagine a cosmic alloy, particles of metal shining through a film of organic dust, a fusion of two worlds. Somewhere between experiment and imagination, researchers began to reconstruct an image of the surface. Not a photograph, but a mental portrait. A dark plane, not smooth but granular, each grain coated with a thin sheen of polymerized carbon, the residue of eons under ultraviolet light. Beneath it, metallic inclusions glint faintly, like embers beneath ash. And when sunlight strikes this surface, it doesn't scatter cleanly. It ricochets between layers, each reflection twisting the light a little more, until its polarization flips. The light we see is not direct, but haunted a ghost of photons that have lost their way. That, I suppose, is why the data felt so intimate. It wasn't just telling us what 3I Atlas was, it was showing us how it had been changed, how the long silence between stars had sculpted even its ability to shine. The polarization curve, deep and asymmetric, was the signature of survival. And then came the anomaly of color dependence. Usually, polarization varies smoothly with wavelength, peaking at shorter or longer bands depending on grain size. But 3I Atlas displayed oscillations, ripples across the visible spectrum, like interference, fringes, that hinted at an ordered structure, perhaps periodic layers or crystalline domains. In simpler terms, its surface might have been patterned, self-organized by thermal stress or by radiation damage. Patterns like that have been seen on tiny scales in laboratory samples of meteorites exposed to ion bombardment, but never before, on a scale so large, on an object drifting freely through space. You know, when you think about it, light polarization is almost like touch. It tells you not what something looks like, but what it feels like, the roughness, the grain, the depth. And the light from 3I Atlas told us that it felt ancient, brittle, alien. It was the texture of something that had endured too much and yet remained intact. What fascinated scientists most was how this deep negative polarization defied the statistical models built from thousands of comets and asteroids. Those models had once seemed universal. The data from 3I Atlas reminded everyone that universality, in astronomy, is always provisional. Every time we think we've mapped the boundaries of behavior, the universe presents an exception, a single object that demands we rewrite the rules. To check for instrumental errors, teams from Japan, Europe, and Chile independently remeasured the polarization angle using different filters. The results were consistent to within a fraction of a degree. This was no artifact. The polarization was real, coherent, and strong. Moreover, it remained stable over time, suggesting that the surface was homogeneous on the scale of observation. In other words, 3I Atlas wasn't tumbling to expose bright and dark regions, it was uniformly strange. Well, that in itself carries a quiet wonder. Uniformity in such an ancient object implies resilience. The same radiation that reshaped its surface might have also annealed it, smoothing variations and erasing scars from its violent birth. Perhaps, over billions of years, the random became ordered. Chaos, polished by time, became harmony. As the data circulated, theorists began to revive an old concept, the idea of interstellar dust agglomeration under electrostatic forces, creating porous but electrically active structures. If 3I Atlas had a surface charged by the solar wind, its interaction with sunlight might have produced polarization effects, amplified by electromagnetic coupling. It's speculative, yes, but no more so than the object itself. When faced with phenomena that don't fit, sometimes speculation is the only bridge to understanding. And that's the thing. The deeper we looked into the light, the more we saw not just a surface, but a history. Every irregularity in the polarization curve was a scar, a memory of collisions, of heat, of radiation. It's humbling to realize that physics remembers, that photons, though weightless, can carry the story of matter across the centuries. Some called the deep negative polarization the fingerprint of elsewhere. Others, more poetically, called it the sigh of another world. Whatever name we give it, it stands as one of the clearest pieces of evidence that 3I Atlas is not just a visitor from afar, but a survivor of conditions beyond our imagination. In one of the final observation sessions, when the object was already fading from view, the polarization signal persisted steady, unwavering, even as brightness declined. It was as if the light itself refused to fade, holding onto its strange character until the very end. And then, quietly, it was gone from our instruments, leaving behind only data and wonder. But science doesn't end with disappearance. Each unanswered question leads to another, deeper one. If the polarization was so profoundly negative, if its cause lay in microstructures or metallic organic hybrids, what did that imply about the processes that formed it? What kind of environment could create such intricate order? To find those answers, we must look not only at a single object, but at the growing collection of anomalies, patterns that, taken together, begin to hint at a broader truth about interstellar matter. And so, as the light of 3I Atlas faded into the background of space, astronomers began to turn from the singular to the statistical, from the marvel of one object to the accumulation of many. Because this was not the only anomaly, there were others, scattered across datasets, each subtle, each improbable on its own, yet together they began to form a constellation of mysteries. And that constellation pointed towards something larger, a pattern emerging from chaos. Perhaps it's time, then, to gather those fragments, to see how the improbable becomes the inevitable when enough of it accumulates. For in the next step of this journey, we move from one anomaly to many, from a single whisper of wonder to the chorus of coincidences that shape our understanding of the rare and the remarkable. Patterns. That is where science begins to breathe. A single anomaly can be dismissed, a quirk of measurement, an imperfection in data, a coincidence. But when anomalies begin to gather, when they echo across different instruments, wavelengths, and observations, something subtle starts to take shape. It's as if the universe clears its throat and whispers, "Look again. The story of 3I Atlas, you see, doesn't exist in isolation. Each irregularity we've traced so far, its missing tail, its metallic heart, its deep negative polarization could, perhaps, be explained away. But taken together, they form a constellation of the improbable, a collection of puzzles that defy easy explanation. It's like seeing stars that don't quite fit the map you've drawn. You can either ignore them or admit the map was never complete to begin with. Well, scientists are careful people. They prefer caution over drama. Yet even the most cautious among them could not ignore how many peculiarities 3I Atlas carried. There were, by conservative count, at least 10. 10 small fractures in our understanding, each widening the more you looked. First, of course, was its origin itself an interstellar visitor, the third ever confirmed. The odds of finding even one such object within the short history of modern astronomy are already small. Finding 3 within a handful of years seemed improbable. Yet here it was, bright enough to catch, strange enough to haunt. Then came the physical irregularities, its unexpected brightness pattern, its absent tail, its unchanging rotation light curve. No matter how close it approached the sun, its reflective behavior remained unnervingly steady, as though the laws of thermal expansion politely passed it by. Third, the mass loss 13%, vanishing without visible emission. Fourth, its composition rich in nickel, poor in water. Fifth, the deep negative polarization, unprecedented among known comets or asteroids. Sixth, the color slope of its light reddish yet metallic, suggesting both organic compounds and high-temperature minerals on the same surface. Seventh, the spectral oscillations across visible and infrared bands, hinting at microscopic ordering unlike anything seen before. Eighth, the lack of rotational variation in polarization angle, implying a uniformly exotic surface. Ninth, its trajectory, slightly perturbed beyond what simple gravitational models predicted, so subtle that it could have been dismissed as noise, but consistent across multiple observatories. And 10th, its long-term fading curve, slower than theory would allow, suggesting that even as it receded from the sun, it was retaining heat or energy in some unknown way. Individually, none of these would overturn a paradigm. Together, They form what physicists call a low probability cluster, a set of unlikely traits that, while each explainable on its own, become statistically absurd when combined. Imagine rolling a die and getting 6 once, that's luck. Rolling it 10 times in a row, that's a message. And that's the thing about improbable coincidences. They don't prove anything, but they invite humility. They ask whether the framework we use to measure normality might be too narrow, too Earth-shaped, too accustomed to the familiar. Perhaps, some said, 3I Atlas wasn't breaking the rules, it was showing us rules we hadn't yet written. In meetings and conferences, scientists discussed this object with a strange mixture of restraint and awe. They would list the facts carefully, noting uncertainties, probabilities, error margins. But beneath that structure, you could sense a quiet thrill, the awareness that something extraordinary was brushing the edge of comprehension. It's not that it violates physics, one astrophysicist said. It's that it dances right at the boundary, where physics still hums but doesn't sing. Statistical reasoning became the battleground. How do you calculate the likelihood of so many independent anomalies occurring together? Some used Bayesian models, layering probability over probability until the combined odds fell below 1 in a billion. Others warned that independence was an illusion, that many of these features might arise from shared causes, but even then, the numbers were unsettling. If such convergence could occur naturally, it would demand a broader, more chaotic universe than we've ever simulated. And yet, the most seasoned scientists insisted on discipline. They reminded everyone of history, how often the improbable had turned out to be mundane once more data arrived. The canals on Mars, the orbit of Mercury, the first pulsar signals, all mysteries once tinged with wonder, later explained with precision. The responsible path, they said, is patience. Wait for the data, refine the models, resist the urge to mythologize. Still, something about 3I Atlas lingered. It wasn't just a statistical outlier, it was an aesthetic one. There was a coherence to its strangeness, a kind of internal logic that made its oddities feel connected. Its composition explained its dryness explained its missing tail, its metallic surface explained its polarization hinted at its age justified its resilience. Everything was improbable, yet everything fit. The universe, it seemed, had conspired to make one perfectly self-consistent enigma. You know, I suppose that's what fascinates us most about anomalies. Not their defiance, but their symmetry. There's beauty in an object that seems wrong, yet remains harmonious within itself. It's like hearing a note outside the scale that somehow resolves the melody. Science, at its heart, is the art of listening for those notes and learning why they sound right, even when they shouldn't. Some voices in the field began to discuss what they called the principle of contextual probability. It's an elegant idea that an event's rarity depends not just on its local parameters, but on the total fabric of reality in which it occurs. In other words, improbable things happen all the time, if the universe is vast enough. When you look across billions of stars, trillions of planets, and eons of time, even the rarest of coincidences become inevitable. Perhaps 3I Atlas was one such inevitability, a cosmic dice roll finally landing on edge. Others disagreed. They argued that science should not retreat into awe, but lean harder into rigor. That every unexplained observation is an invitation not to romanticize, but to measure more carefully. They weren't wrong. Without skepticism, discovery becomes belief. But without wonder, skepticism becomes blindness. The balance between the two is what makes astronomy both science and story. To test how unlikely this confluence truly was, teams built computational models of thousands of synthetic interstellar objects, each with random combinations of material, spin, and trajectory. Out of tens of thousands of trials, only a handful produced the kind of data 3I Atlas had. Even then, those simulated objects required conditions rarely seen: rapid temperature gradients, exotic metal ratios, or unique rotation dynamics. In the sterile arithmetic of simulation, the odds of encountering such an object were almost vanishing, and yet we had. Perhaps it's human nature to assign meaning to rarity. When something improbable happens, we feel compelled to ask why it happened to us, now, here. But the universe is indifferent to timing. Its improbabilities are simply the natural overflow of its vastness. Still, it's hard to look at something as strange as 3I Atlas and not feel as though we're being shown a page from a much larger book, one whose language we're only beginning to learn. Well, if we follow the mathematics, probability doesn't dictate truth, it only guides curiosity. An event that seems statistically impossible can still happen once, and that once is enough to demand understanding. That's why science never ends with a shrug. Even if every anomaly of 3I Atlas can someday be explained by natural processes, the path toward that explanation will have expanded what we call natural. In one memorable discussion at a symposium, a scientist compared it to a violin string vibrating beyond its fundamental tone. When you pluck it hard enough, she said, you hear harmonics notes that aren't supposed to exist, but do. They remind you that the string is more complex than its simplest sound. 3I Atlas, she suggested, was the harmonic of the solar system, a reminder that our cosmic instruments can still produce unexpected music. And maybe that's the most honest way to see it. The improbable is not an exception to the rule, but a sign that our rules are written in pencil. The anomalies are corrections, not contradictions. They force us to look closer, to sharpen our definitions of what's ordinary. In time, this growing collection of peculiarities began to be catalogued, compared, connected. Astronomers started cross-referencing data from all known interstellar visitors, looking for shared traits. Early patterns emerged: higher reflectivity than expected for their size, muted thermal emissions, hints of metal-rich composition. Each new visitor seemed to carry a trace of 3I Atlas's signature, as though they were members of the same lost family remnants of planetary systems long gone, scattered through the galaxy. The term interstellar archetype began to appear in papers, cautiously at first. The idea that there might exist a whole class of objects with shared anomalies, dense, metallic, chemically parched, optically peculiar, was both thrilling and daunting. Because if that were true, it would mean our solar system, with its wet, icy comets, is not typical but provincial. We may be the outliers, and that thought changes perspective entirely. It reminds us that probability is always local. What feels rare from where we stand might be common elsewhere. The extraordinary could be ordinary under another sun. But for now, on this small planet, with our small instruments and brief window of observation, we hold only fragments. We see the improbable, we measure it, we argue about it, and in doing so, we inch closer to the truth. Not the final truth, there's no such thing but a clearer one. And as the community wrestled with how to interpret these coincidences, a deeper question began to form, not about the object, but about ourselves. How should science respond to rarity? How do we guard against the allure of the extraordinary without blinding ourselves to its possibility? That tension, the pull between skepticism and wonder, has shaped every great discovery in history. And so, from the cluster of improbabilities surrounding 3I Atlas, we turn now to the quieter, more philosophical struggle that follows it, the human struggle to remain grounded while facing the unknown. The next step in this story, then, is not about data, but about discipline, the conservative heart of science, and the reason its caution is not a weakness, but its strength. Caution has always been the quiet backbone of science. The universe is vast, unpredictable, and often deceptive. For every spectacular discovery that reshapes our understanding, there are hundreds of illusions, artifacts of noise, bias, or incomplete data. That's why the scientific method insists on restraint, to not confuse what dazzles the imagination with what endures the test of evidence. And that is precisely where the story of 3I Atlas now rests, in the careful, almost sacred balance between wonder and skepticism. You see, the discipline of astronomy has learned humility from centuries of false dawns. There was a time when the canals on Mars were thought to be proof of civilization, when the flickering of distant stars was read as messages, when cosmic rays were interpreted as whispers from creation. Each time, the pattern resolved into natural causes, fascinating, yes, but not miraculous. And so, when a new enigma arrives, one that tempts us with extraordinary implications, science reflexively steadies its pulse. It says, wait, let's test the ordinary before we dream of the impossible. That's the foundation of what we call the conservative stance in science. It isn't cynicism, it's discipline. It's the refusal to let curiosity outrun evidence. In the case of 3I Atlas, this meant that, despite the cascade of anomalies, the default assumption remained that the object was natural, a fragment of some ancient system, shaped by familiar processes, under unfamiliar conditions. It was not dismissed as alien or artificial, not because that idea was impossible, but because it wasn't necessary. In science, necessity is the measure of truth. If known physics can explain what we see, even barely, that is the explanation we hold until something breaks it beyond repair. Well, perhaps that sounds unromantic. But in truth, it is one of the noblest qualities of the scientific mind, the readiness to be patient, to wait for better data, rather than rush into glory. You might say that skepticism is not the opposite of wonder, it is its guardian. Without it, we would drown in fantasies. So, when astronomers looked at the strangeness of 3I Atlas, the missing tail, the metallic surface, the deep negative polarization, they reminded themselves that every outlier begins as a misunderstanding. Maybe the data were incomplete, maybe the models were wrong, not the universe. Maybe this was not a messenger from another civilization or a cosmic oddity, but simply a kind of body we hadn't sampled yet. After all, our entire understanding of comets and asteroids is drawn from a few thousand examples in one solar system, a single neighborhood among hundreds of billions. What arrogance, really, to assume the diversity of the cosmos fits inside our catalogues. That humility drives the conservative approach. When confronted with anomalies, the first question is not, what new phenomenon have we found, but what have we overlooked? Could the tail have been obscured by geometry? Could the mass loss be explained by non-volatile erosion? Could the negative polarization arise from metallic microstructures formed naturally over eons? Each question anchors speculation to reason. And yet, this caution carries its own quiet danger. There is a kind of comfort in disbelief, a safety in assuming the universe will never surprise us too much. Scientists are trained to avoid extraordinary claims because extraordinary evidence is so hard to come by. But the paradox is that sometimes, by avoiding the extraordinary, we risk missing the truth when it does arrive. The line between prudence and blindness is thin, and the story of 3I Atlas walks it carefully. Still, the community largely held the line. The hypothesis that the object was natural remained the baseline, the null. A hypothesis. Everything else had to prove itself against it, and that's how it should be. Because to overturn a natural explanation, you need not just curiosity, but a mountain of data and a chain of reasoning stronger than doubt. To understand why that standard is so high, consider the history of cosmic anomalies. When pulsars were first detected in 1967, their rhythmic radio pulses seemed too precise, too regular to be natural. For a moment, the discoverers nicknamed them LGM, Little Green Men. But soon, theory caught up. Those signals turned out to be neutron stars, the collapsed hearts of dead suns, spinning hundreds of times per second. Nature, once again, had proven stranger than imagination, but still within its own laws. That's the pattern. Every time we think we've glimpsed intelligence, we find instead a deeper layer of natural complexity. So when 3I Atlas entered the scene, gliding silently through the inner solar system with its improbable chemistry and behavior, many scientists smiled at the déjà vu. "We've been here before," they said, and they were right. The sensible stance was to assume the universe was once again outsmarting our expectations, not breaking them. The small sample size reinforced that caution. 3 interstellar visitors, Oumuamua, Borisov, and now Atlas, do not make a pattern large enough for sweeping conclusions. They are single pages torn from a book we haven't read. To draw grand inferences from so few examples would be like defining the ocean by 3 waves. And yet, every scientist knows that progress begins with fragments. The challenge lies in holding those fragments lightly, believing in their significance, but not mistaking them for the whole story. One astronomer put it beautifully. We are learning to listen to interstellar objects the way a child listens to a new language, one word at a time, uncertain of meaning, but certain it matters. That's the posture of scientific conservatism at its best, not denial, but patience. There's another reason caution is essential: bias. Humans are pattern-seeking creatures. We find meaning in noise, faces in clouds, purpose in randomness. In the realm of cosmic observation, that instinct becomes both gift and curse. The instruments we use, the algorithms that filter data, even the way we visualize results, all are prone to amplifying what we want to see. A faint streak might become a tail. A spectral dip might suggest an element that isn't there. That's why reproducibility, seeing the same thing with different tools, different teams, different methods, is the bedrock of certainty. For 3I Atlas, that process is ongoing. Data from the Tianwen-1 orbiter, ground-based telescopes, and infrared observatories still need to converge before anyone can claim more than curiosity. And so the conservative stance endures. 3I Atlas is natural until proven otherwise. Perhaps it represents a new class of interstellar body, forged under conditions unfamiliar but not supernatural. Perhaps it is part of a spectrum of matter we have simply never sampled. The cosmos, after all, doesn't owe us familiarity. But here's the quiet irony. This insistence on natural explanations is not a rejection of wonder. It's the very thing that keeps wonder honest. Because if every mystery were answered by invention or myth, discovery would end. Only by exhausting the ordinary can we ever earn the right to reach for the extraordinary. That's the discipline that built modern science, a faith, paradoxically, not in certainty, but in process. Still, even the most steadfast skeptic can feel the pull of possibility. Late at night, when the data screens dim and the equations pause, one can imagine the scientists who worked on the Tianwen-1 project staring at those images of 3I Atlas, feeling something ancient stir. It's not belief, exactly. It's recognition, the sense that we are witnessing, something just beyond comprehension, something that humbles us back into silence. That humility, too, is part of the conservative view. It acknowledges that the unknown is not a failure but a teacher, that every unanswered question is a reminder of how little we truly control. To say, "we don't know," is not defeat, it's an act of honesty. The conservative scientist holds that phrase sacred, for it's what keeps knowledge alive. And perhaps, in a broader sense, that's what 3I Atlas offers us, a lesson in restraint. It reminds us that we are still at the beginning of interstellar astronomy, standing on the shoreline of a vast sea. We have only dipped our toes, and already the waves look strange. The temptation is to dive headlong into speculation. The wiser path is to wade slowly, to feel the currents, to map the depths inch by inch. You know, there's a beauty in that patience. The universe is not in a hurry to reveal itself, and perhaps neither should we be in a hurry to define it. Every anomaly, every irregularity is a conversation, one that can last decades, even centuries. And so, scientists record, compare, question, refine. Step by step, they build a foundation strong enough to bear the weight of wonder. And yet, as the dust of caution settles, another kind of voice begins to rise, a gentler one, but equally vital. It asks whether restraint alone can lead us forward, whether too much skepticism can, in its own way, become a cage. Because curiosity needs room to breathe, imagination needs permission to explore. To balance that freedom with rigor, to be open but not reckless, that is the next challenge. So as the conservative stance secures its ground, a new perspective begins to take shape beside it, one that honors evidence, but also honors the power of questioning itself. It's the posture of minds willing to entertain the unlikely, not as truth, but as possibility. And it belongs to a new generation of thinkers, those who, while grounded in data, are unafraid to look up and wonder aloud. That, I suppose, is where our journey turns next to those who argue not against skepticism, but for a more curious kind of caution. To the voices who say that the unknown is not a wall to defend against, but a horizon to approach with care. And so, as we continue, the conversation shifts from the guardians of restraint to the explorers of possibility. There comes a moment in every great scientific story when the pendulum begins to swing the other way, when caution, though noble, begins to feel like hesitation, and someone dares to ask, quietly but insistently, what if? That question is both a risk and a gift. It's the spark that keeps knowledge from calcifying into dogma. And in the strange case of 3I Atlas, that question came from voices not defying science, but expanding its boundaries, voices like that of Avi Loeb. Loeb, a Harvard astrophysicist known for both his brilliance and his willingness to wander into controversial territory, has long argued that scientific openness should not be mistaken for recklessness. His view is simple, even old-fashioned. We should follow evidence wherever it leads, even if it leads us to uncomfortable possibilities. After all, the history of discovery is a history of discomfort, of ideas once dismissed as absurd that later became foundations of truth. But he also reminds us that imagination must always be disciplined by data. There's a difference between proposing and proclaiming, between wondering aloud and declaring belief. In the context of 3I Atlas, that distinction mattered deeply. The object's anomalies tempted speculation, its metallic composition, its absence of a tail, its improbable trajectory. But speculation, when done well, is not wild, it's structured curiosity. Loeb and others like him advocate for a kind of intellectual openness that invites new hypotheses without surrendering to fantasy. They argue that science should not just explain the universe, but listen to it, to really listen, especially when it speaks in strange tones. You see, curiosity is not the enemy of rigor, it is rigor's engine. The greatest scientists in history, Galileo, Newton, Einstein, were not conservative thinkers, at least not in their hearts. They questioned the axioms of their age, but they did so through the language of proof. What Loeb and his contemporaries propose is a modern echo of that spirit, a controlled openness, one that treats the extraordinary not as taboo, but as testable. Perhaps that's what 3I Atlas demands from us. Not credulity, but courage. The courage to ask questions that make others uneasy. Could it represent a type of object our current models cannot yet predict? Could it, in some remote possibility, be a fragment of something designed rather than born? The conservative scientist will say, we have no evidence for that. And they are right. But the open-minded one replies, true, but we also have no evidence against it. Between those two truths lies the fertile ground where discovery grows. And that's the thing about intellectual openness. It's not about believing more. It's about forbidding yourself to believe less than the universe deserves. To keep the door unlocked, even if you never expect anyone to walk through. Still, Loeb's perspective is not without criticism. Many accuse him of courting speculation, of drawing public attention to possibilities that outpace evidence. But perhaps that discomfort is part of the process. The tension between restraint and imagination has always been the pulse of science. Without restraint, we fall into myth. Without imagination, we stagnate. Somewhere between those poles lies the narrow bridge of progress, and walking that bridge requires both caution and daring. You know, when I think about it, I suppose the act of looking up at the stars is itself an act of openness. The night sky invites us not just to measure, but to wonder. And in that wonder lies a kind of truth no data set can replace. The acknowledgement that we do not yet know everything, and that ignorance, rather than shameful, is sacred. The scientists who advocate for a more open stance toward anomalies like 3I Atlas often use the phrase epistemic humility. It's a mouthful, but it means something profoundly human. To admit that our knowledge, vast as it seems, is still a flicker against the dark. That humility is not a weakness, it's a compass. It points us not toward certainty, but toward curiosity. And curiosity, when practiced responsibly, can lead to revolutions. Consider the great paradigm shifts of history. When Copernicus dared to move Earth from the center of the cosmos, he didn't have the final proof. When Darwin spoke of evolution, he couldn't yet explain the mechanism of heredity. When Wegener proposed continental drift, his contemporaries mocked him for lack of data. Each was accused of overreach. Each was later vindicated by evidence that didn't yet exist when they first asked, what if? Openness, then, is not about being right, it's about being ready. In that light, the question of 3I Atlas becomes less about what it is and more about how we approach what we do not understand. Some scientists look at it and see a statistical outlier, a rock behaving oddly. Others look and see an opportunity, a reminder that our models, elegant though they are, might still be blind to entire categories of matter and motion. Loeb's approach does not claim certainty, it claims curiosity. He says, let's not assume the universe is already mapped. The controversy around such openness is, in itself, healthy. It forces the community to sharpen its reasoning, to define more clearly what constitutes evidence, to draw the line between possible and probable. In doing so, both sides, those of caution and those of curiosity, elevate each other. One protects against folly, the other against fear. Science, after all, is not a fortress but a dialogue, and the strength of that dialogue depends on both voices being heard. Perhaps the real lesson of 3i Atlas is that science needs its dissenters, the dreamers, who refuse to let the unknown become invisible. Every field has them, those who step slightly outside the mainstream, not to defy it, but to remind it that the edges exist. Without them, the map would never expand. There's a phrase Loeb once used that lingers in my mind. When you are walking in a dark forest, you should not close your eyes for fear of seeing shadows. It captures the essence of controlled openness. To look bravely into the dark, but not to mistake every rustle for a ghost. To explore without expectation, to question without claiming. That's what true scientific courage looks like. And perhaps this courage is precisely what the next age of astronomy will require. As we enter the era of interstellar discovery, our instruments will reveal more and more objects that defy our templates. Some will look wrong, some will behave wrong, some will whisper of conditions no model can yet describe. The challenge will not be in collecting data, it will be in staying open to interpretation without falling into illusion. The line between skepticism and wonder will need constant redrawing. The virtue of not knowing, then, becomes central. To say we don't know is not an admission of failure, but a declaration of readiness. It is the moment before discovery, the breath before revelation. In the case of 3i Atlas, the data remain incomplete. There are gaps in understanding that no telescope, no simulation can yet fill. But those gaps are not voids, they are invitations. They remind us that mystery is not an obstacle but a frontier. And perhaps that is what this whole debate between the cautious and the curious is truly about. It's not a war of ideas, but a rhythm, a breathing pattern that keeps science alive. Exhale, doubt, measure, verify. Inhale, wonder, imagine, propose. Both are necessary. Without one, the other suffocates. You know, I suppose that's the beauty of a field like astronomy. It's a science born of looking up, of staring into darkness, and finding not fear but fascination. To explore the cosmos is to accept contradiction, to hold logic in one hand and awe in the other, and to understand that both are forms of truth. As 2025 unfolds, new instruments, space telescopes, planetary probes, massive observatories will begin to extend our reach into the interstellar realm. Each will bring more data, more anomalies, more questions, and when they do, this conversation between restraint and curiosity will continue. Because science, at its core, is not a collection of answers, but a process of learning how to ask better questions. And perhaps, as we move forward, that's the real legacy of thinkers like Loeb. Not that they claim to know more, but that they remind us it's all right to admit how much we don't know, to keep the doors open, but the floors steady. To listen to the universe not as skeptics or believers, but as explorers who understand that discovery is never the end. It's the beginning of a deeper kind of ignorance, the kind that humbles us into wonder. And as that balance continues to shape the dialogue around 3i Atlas, the question naturally widens beyond science itself. Because what we learn from these objects is not only about other worlds, but about ourselves, about the way we approach the unknown, the way we define truth, the way we respond when the universe refuses to fit the patterns we expect. And that leads us gently toward the next reflection, one that steps beyond the laboratory and into the human heart, toward what these discoveries mean for our species, for our sense of place, and for the fragile wisdom that binds us to the cosmos itself. When we step back from the equations, from the spectra, probabilities and models, what remains is something quieter, but no less profound, a question not just about what 3i Atlas is, but about what it means. Because every so often, science gives us a moment that transcends its own mechanics, a moment that reminds us that discovery is not just an act of measurement, but a mirror held up to ourselves. 3. I Atlas is one of those mirrors. It arrived in our solar system silently, without warning, an uninvited guest from another star. And for a brief time, it became the focus of thousands of human minds scattered across the planet, united by curiosity. Engineers in Beijing, astronomers in Hawaii, data analysts in Europe, all staring at the same faint speck of light, all asking the same simple, impossible question, what is it? You see, that's the beauty of moments like this. In a world so divided by borders and noise, an interstellar visitor can make us pause, look upward, and remember that we share a single sky. 3. I Atlas. In its quiet way, pulled humanity out of its orbit of daily concerns and reminded us of scale. It reminded us that our small blue planet is part of something unimaginably vast, that the universe is not a distant backdrop, but a living context in which we are still learning to exist. The mystery of this object, its missing tail, its alien composition, its strange light, became a metaphor for something larger, the humility of not knowing, and the grace of seeking anyway. Well, perhaps that's why such discoveries linger, not because of what they reveal, but because of how they change the way we see ourselves. There's something deeply human about our impulse to investigate the unknown. Long before telescopes or probes, we stared at the night sky with questions we didn't have words for. And now, with all our instruments and algorithms, we are still asking the same questions, only in higher resolution. We are, in essence, the same species that once painted constellations on cave walls, only now we paint them with data and code. When scientists say that we are at the dawn of interstellar astronomy, they don't mean just technologically, they mean philosophically. We are standing at the edge of a new kind of awareness, the realization that our solar system is not an isolated island, but part of a grander ocean of planetary systems, each with its own chemistry, its own logic, its own history. 3. I Atlas is one of the first drops from that ocean to reach us. And in studying it, we begin to glimpse the cosmic pattern of which we are a part. You know, I suppose that's what moves me most about this story. That somewhere in another corner of the galaxy, billions of years ago, a world may have formed, lived, and shattered. And now, a fragment of that lost world has drifted all the way here, crossing light years of emptiness to brush past our Sunday. For a few brief months, it reflected our star's light before vanishing again into the dark. We measured it, catalogued it, argued over it, but in the end, it was simply a messenger. And what it told us was not about itself, but about the nature of connection. Because in studying 3I Atlas, we are also studying our own beginnings. Every element in our bodies, iron, carbon, oxygen, was once formed in a star that lived and died long before Earth existed. We are, quite literally, interstellar matter that learned to look back at the stars. So when an object like Atlas enters our solar system, it is not a stranger, it is family returning home. Its atoms are kin to ours. The light it reflects is the same light that feeds our planet. And the questions it provokes are the same questions that define us. Where do we come from, and how far can we understand? There's a strange tenderness in that realization. Science often seems detached, cold, rational, but beneath its precision lies a deep emotional truth. The desire to understand is an act of love. Every equation written, every telescope pointed skyward, is a gesture of reverence. To study the universe is to say, in our own human way, we see you. And perhaps that's why the interstellar age feels so momentous. For the first time in history, we are not just looking at the stars, we are receiving pieces of them. Each object that drifts into our system is like a letter from another world, written in the language of chemistry and light. 3I Atlas, with all its peculiarities, may one day help us understand how planets form, how matter behaves under alien suns, how common or rare our own kind of world might be. But even before those answers arrive, it has already given us something equally valuable, a sense of belonging to the cosmos itself. When people talk about the limits of human understanding, they often imagine a wall, the edge of what we can know. But in truth, knowledge doesn't end. It just becomes more subtle, more complex. Every answer opens a dozen new questions. That's the rhythm of discovery. And 3I Atlas, in its enigmatic silence, fits perfectly into that rhythm. It doesn't shout its meaning, it whispers it. And its whisper says, keep going. Perhaps that's what makes interstellar astronomy feel so different from all that came before. We are not exploring territory now, we are exploring perspective. The telescope is no longer just an instrument, it's a mirror, reflecting our curiosity. The unknown out there becomes a reflection of the unknown within us. And yet, there is also something humbling in how little we can do. For all our technology, we cannot touch 3I Atlas, cannot sample its surface, cannot follow it into the dark. We must infer its story from faint photons and subtle variations in light. It's a reminder that knowledge is often indirect, built from patience and imagination. The universe rarely speaks plainly. It speaks in riddles, and understanding is an act of translation. Still, even through that limitation, something remarkable happens. Data turns into dialogue. Each observation, each strange dip in brightness, each spectral irregularity becomes a sentence in a conversation that spans across time and distance. When scientists analyze those signals, they are not just doing calculations, they are, in a way, listening to the universe, remembering itself. There's a quiet optimism in that thought. For centuries, humans have looked outward in search of meaning through myth, through religion, through science. But perhaps meaning was never out there to be found. Perhaps it emerges in the act of looking itself. 3. Atlas didn't come to teach us something specific. It came to remind us that curiosity is a form of grace. To wonder is to participate in the unfolding of creation. And if we take that seriously, if we see these interstellar visitors not as curiosities but as chapters in a shared cosmic history, then astronomy becomes something more than observation. It becomes empathy at a universal scale, the understanding that every world, every star, every drifting fragment, no matter how distant, is part of one great narrative, the story of matter striving toward consciousness. When we speak of being at the dawn of interstellar astronomy, it's not just about technology, it's about awakening. We are beginning to see ourselves not as inhabitants of one solar system, but as citizens of the galaxy. The data we gather today, the signals we decode, the models we build, all of it is laying the foundation for a new kind of cosmic identity. In 2025, as new observatories prepare to scan the skies with unprecedented sensitivity, that identity is deepening. We are learning not only to observe the universe, but to listen to it with humility, to read its silences as carefully as its light. You know, it's easy to think of science as progress a ladder, climbing upward towards certainty. But perhaps it's more like a spiral, moving outward, circling back, expanding perspective rather than conquering mystery. 3. Atlas doesn't give us answers, it widens the circle. It teaches us that mystery is not the opposite of knowledge, but its companion. Without the unknown, discovery has no horizon. And so, the meaning of this interstellar object is not confined to physics or chemistry, it's philosophical. It asks us to reconsider what it means to be human in a universe that is not centered on us, that operates on scales of time and distance we can barely imagine. It humbles us, but it also ennobles us. For even though we are small, we are capable of understanding that smallness, and that understanding is its own kind of greatness. Every generation of humanity inherits a different kind of sky. Ours is one where the boundaries between stars are beginning to blur, where the universe is no longer a distant spectacle but an active participant in our story. 3. Atlas is a reminder that we are still at the beginning of that story, still learning the alphabet of the cosmos. What we call anomalies today may be commonplaces tomorrow. What seems miraculous now may, in time, become ordinary, but the awe that will remain. And perhaps that is the true gift of this encounter, to remind us that the universe, for all its silence, is generous. It keeps sending us questions, knowing that the act of answering them makes us more alive. As the light of 3I Atlas fades into the archives, as the data settles into models and reports, we are left not with closure, but with continuity. The questions it raised will ripple through generations of research. Young scientists who saw its image for the first time will one day be the ones to interpret the next interstellar visitor. Each discovery will build upon the last, a chain of curiosity stretching across centuries, and that continuity carries us gently toward the next reflection, toward a more personal inquiry. If this interstellar fragment has shown us our place in the cosmos, then where, exactly, do we stand within that vastness? How do we reconcile our fragility with our yearning to understand? That is the question that awaits us next, the question of who we are, not just as observers, but as participants in the grand unfolding of the universe. When we ask where we stand in this story, we are not asking about geography, but about perspective, because the story of 3I Atlas, like every great scientific mystery, is as much about us as it is about the cosmos. It is not just a tale of distant rock and light, it is a reflection of how humanity meets the unknown, how we think, how we doubt, how we learn. In its silence, 3I Atlas has become a kind of mirror, showing us the posture of our own curiosity. You see, the deeper we study the universe, the more it studies us back. Every discovery we make tells us something not only about the stars, but about the limits and strengths of our understanding. And when faced with something we cannot fully explain, our reactions, caution, excitement, skepticism, imagination, reveal who we are at the frontier of knowledge. In that sense, the question of where we stand is a question about method, not belief. Because the great challenge of our time is not whether we will find life, or intelligence, or meaning among the stars. It is whether we can continue to seek truth without losing humility, whether we can stand before the unknown with both discipline and awe. Perhaps, then, the real measure of progress is not how much we know, but how we behave in the presence of what we do not know. When 3I Atlas crossed our system, we saw the best and the worst of our intellectual instincts at play. Some rushed toward conclusions, weaving stories out of shadows. Others held so tightly to skepticism that they risked becoming blind to wonder. Between those extremes lies the narrow ground where real science grows curious, cautious, endlessly self-correcting. Well, I suppose that's where we stand now, on that narrow ground, balanced between certainty and mystery, between the human desire to explain and the human need to imagine. And the balance itself is fragile. It requires patience, honesty, and a kind of moral discipline. To do science well is not merely to measure, it is to learn how to listen without pretending to hear what we want. When we look at 3I Atlas, we are reminded that the universe is not obligated to make sense to us. Its laws are consistent, yes, but our understanding of them is provisional, an evolving translation of something vast and subtle. Every time we think we've built a perfect model, nature shows us an exception, as if to say, there's more. The cosmos is not a problem to be solved, it's a relationship to be tended. And that's the thing. Humility is not weakness in science, it is structure. It's what keeps knowledge honest. To admit uncertainty is not to give up, it's to clear space for discovery. In a way, 3I Atlas has given us that gift. It has humbled us. It has reminded us that we are still beginners, even after centuries of looking upward. You know, when I think about humanity's place in this story, I often imagine the timeline of the universe compressed into a single year. In that scale, all of human history fits into the last few seconds before midnight on December 31st. Every civilization, every theory, every observation, all of it flashes by in an instant. And yet, in those seconds, we have managed to look beyond our planet, to find other worlds, to listen to the faint signals of galaxies billions of years old. We may be latecomers to cosmic time, but we are attentive ones. So, where do we stand? We stand at the beginning. We are the children of a young species learning to see clearly for the first time. Our telescopes are our first words, our equations, our first sentences. We are trying to describe something infinite in a language still being invented. And every object like 3I Atlas adds a new word to that language, a syllable of understanding carved from silence. But standing at the beginning also means accepting that the horizon will always recede. No matter how far we reach, the unknown will remain ahead of us. That's not failure, that's design. The pursuit of knowledge is infinite because reality is infinite. The joy of discovery lies not in arriving, but in realizing there is always more to discover. Perhaps that's why science feels spiritual at times, not because it answers the great questions of existence, but because it keeps them alive. The discipline of evidence and the humility of uncertainty are, in their own way, acts of reverence. When we calculate the orbit of an interstellar object or analyze its light, we are participating in a conversation that began long before us and will continue long after. We are adding our verse to the universe's unfinished poem. And that poem is not written in the language of certainty, but of attention. It asks us to be precise, but also patient, to care for truth as one would care for a fragile flame. 3. Atlas teaches us that to study the cosmos is to practice both courage and restraint. The courage to ask, what if? And the restraint to wait for evidence before answering. There's another lesson here, subtler but no less important, that knowledge is communal. No single person, no single nation can own discovery. When the Chinese Mars orbiter captured the image of 3I Atlas, it did more than record data, it extended an invitation. It reminded us that exploration belongs to all of humanity. Each observation, no matter who makes it, becomes part of a shared archive of wonder. Perhaps then, the real power of these discoveries is not in their conclusions, but in their capacity to unify. In a world often divided by noise and urgency, the cosmos remains impartial. It does not favor language or ideology, it rewards only curiosity. To look up together is to remember that we are all, fundamentally, the same kind of creature, temporary, fragile, yet capable of awe. In 2025, as new observatories prepare to map the heavens with unprecedented detail, we stand on the threshold of a deeper connection between technology and humility. The tools we've built, massive mirrors, orbiting cameras, quantum sensors are extensions of our senses, but they are also reminders of our limits. The more we see, the more we realize how little we have seen. Every answer enlarges the question, and so, perhaps, the meaning of where we stand is not fixed. It shifts with every discovery. Today we stand between the known and the unknown. Tomorrow, that boundary will move. What matters is not the position itself, but the posture we maintain while crossing it. Do we walk with arrogance or with wonder? Do we treat the unknown as a threat or as an invitation? Well, I suppose that's the heart of the question. The universe is vast, indifferent, and ancient, but it is also generous. It keeps offering us chances to rediscover our place, to grow wiser, to learn humility through awe. 3. Atlas was one such chance, and there will be others. Each will challenge our models, our patience, our imagination. Each will ask us to decide again what kind of explorers we wish to be. And maybe that's the quiet answer to where we stand. We stand in motion. Not at the center, not at the edge, but in the flow between ignorance and understanding. The universe moves through us as much as we move through it. Our task is not to conquer it, but to learn how to listen while it speaks. In the end, standing in this place between certainty and wonder, between data and mystery, defines us more than any single discovery ever could. For it is here, in this fragile balance, that humanity becomes what it was always meant to be, a species aware of its smallness, yet unafraid to reach beyond it. And as that awareness deepens, another realization begins to form, one that bridges the scientific with the personal. If we are to continue exploring, not just outward, but inward, then our tools must evolve alongside our understanding. The next chapter in this story is not only about the cosmos we observe, but about the instruments we build to see it more clearly, and the disciplines we must strengthen to interpret its voice with honesty. From here, the story turns toward that practical frontier, the art and rigor of observation itself. Observation is the art of attention. It's the bridge between the mind and the universe, the discipline that turns wonder into understanding. And in the case of 3I Atlas, that bridge was built from many directions at once: images, spectra, polarization data, and dynamic modeling, all converging toward one fragile truth. Each method on its own tells only part of the story, but together they form something greater than the sum of their light. You see, the cosmos does not yield its secrets easily. It speaks in multiple languages at once, and to listen properly, we must learn to hear them all. The image from Tianwen-1, for example, captured the geometry, the visible face of a traveler illuminated by sunlight. From it, we learned the shape, the reflectivity, the curve of its brightness as it spun. But images alone are only the skin of reality. Beneath that surface, spectra told a deeper tale. The composition, the minerals, the subtle play of metals and silicates encoded in color and frequency. Meanwhile, polarization, the strange twisting of light's orientation, whispered of texture, of grain and roughness, of the microscopic world that shapes reflection. And then came the dynamic models, where gravity, heat, and spin all dance together to predict motion, revealing the inner structure through the way an object moves. This, perhaps, is the quiet revolution of modern astronomy, the realization that no single form of seeing is enough. To know something cosmic, we must triangulate across its manifestations, stitching the physical, the chemical, and the optical into a single coherent fabric. That's what the study of 3I Atlas demanded: a symphony of instruments working across continents and orbits, each refining the other's mistakes. Because, well, every instrument lies a little. Every detector carries its biases. The camera flattens, the spectrometer stretches, the models simplify. But when their errors overlap, patterns emerge. A false signal in one dataset can be cancelled by the precision of another. The art lies in knowing how to weave the imperfections into a clearer whole. That's what astronomers call multi-platform observation, not just many eyes, but many perspectives of truth. Take, for instance, the challenge of measuring brightness from an interstellar object that's fading faster than it moves. A single telescope cannot track it long enough to form a continuous curve. The night sky moves, weather interferes, daylight interrupts, but when observatories share data, Chile handing to Hawaii, Hawaii handing to La Palma, the rotation of the Earth becomes an ally. The planet itself becomes a telescope, its surface turning like a shutter across the heavens. And when orbiters like Tianwen-1 add their view from beyond Earth's atmosphere, the network closes its circle. Together, they create a temporal bridge across time zones and wavelengths, making the invisible visible. That collaboration isn't merely technical, it's philosophical. It embodies the very principle that knowledge is collective. No single nation or instrument owns the sky. The cosmos is democratic. It shines for everyone who looks. 3I Atlas reminded us of that truth, because only through shared observation could its story begin to cohere. Still, the complexity of integrating such data is staggering. Imagine aligning images taken through different atmospheres, under different conditions, with different resolutions, each affected by distortions of light and movement. Even the smallest calibration error, a fraction of a pixel, a degree of polarization, can ripple through analysis and change conclusions. Scientists must therefore build rigorous frameworks of correction. They account for telescope tilt, sensor temperature, dust scattering, even the color of airglow above the horizon. The process is not glamorous, but it is sacred, because in the end, every photon must be earned. You know, I suppose that's what makes astronomy both fragile and profound. It's an act of faith in precision. We stare across billions of kilometers, chasing whispers of light that have traveled for ages, and we dare to interpret them through mathematics. And yet, remarkably, it works. Within those faint signals, we find fingerprints of atoms, the tempo of rotation, the memory of heat. The universe leaves its autobiography in light, and our instruments are its translators. In the study of 3I Atlas, one of the great lessons was how complementary these methods truly are. The spectral data revealed that nickel dominated over iron, but polarization confirmed that those metals were bound into microstructures rather than smooth plates. Dynamic models then showed that its mass distribution was too irregular for a homogeneous body. It must have been fractured within, a lattice of denser cores and porous gaps. Only by combining those strands did the picture come alive, a metallic fragment, ancient and battered, with a surface hardened by radiation and an interior honeycombed by lost volatiles. And yet, for all this complexity, the greatest obstacle wasn't the mystery itself, it was the noise. Systematic errors creep into even the most careful experiments. The human eye sees patterns where there are none. Instruments amplify signals that aren't there. Sometimes the most courageous thing a scientist can do is erase what they thought they saw. That humility is the heart of multi-platform work, to accept that no single dataset is pure, but together they can be trusted. This philosophy extends beyond telescopes. In modern astrophysics, simulation is now a kind of observation too. Supercomputers recreate the conditions of the early universe, test hypotheses, and compare outcomes with the sky. If the simulation matches the data, we gain confidence. If it diverges, the model changes. It's an iterative loop. Observe, simulate, compare, refine, a kind of cosmic heartbeat. 3I Atlas, with its peculiar traits, became a perfect test case for this method. The models of heat flow, radiation pressure, and particle dynamics were pushed to their limits, and each adjustment nudged theory closer to truth. Perhaps this is the quiet genius of modern science. It learns through error, not in spite of it. Mistakes are not failures, they are coordinates. Each tells us where understanding breaks, and thus where discovery begins. 3I Atlas forced astronomers to confront those boundaries, to question their instruments, to recalibrate not just their data, but their assumptions. In doing so, it sharpened the collective vision of a field that is learning to see in higher dimensions. Well, the lessons from that effort extend far beyond one object. They speak to a new way of exploring the cosmos, one that blends observation with computation, collaboration with humility. It's no longer enough to look. We must also integrate, compare, cross-check, and listen. Each observation is a fragment of a larger narrative, and the art lies in weaving those fragments into a coherent story without forcing the pattern to fit our preconceptions. For example, when the first reports came in about the negative polarization of 3I Atlas, some dismissed it as instrumental error. Others believed it revealed a new kind of material. Instead of choosing sides, the community built a layered verification system. Optical measurements were compared with infrared reflections. Independent teams repeated the analysis using different instruments. Only when the anomaly persisted across all platforms did consensus begin to form. That is how science protects itself from the seduction of the extraordinary, through redundancy, through dialogue, through the humility of repetition. At its best, this process becomes something almost poetic, a choreography of truth. One instrument observes, another questions, a third refines, and together they converge toward clarity. It's a slow dance, measured in years, sometimes decades, but in that patience lies integrity. The cosmos, after all, moves at its own pace. In 2025, the field of astronomy is standing at a crossroads where technology and philosophy intertwine. The next generation of observatories, the Rubin, the Roman, the Vera C, Rubin Observatory in Chile, and space-based telescopes orbiting Earth and Mars will operate not as isolated instruments, but as nodes in a single living network. Each will monitor the sky continuously, exchanging data in real time, correcting one another's biases. This is the future of observation, not isolated eyes, but a shared vision, planetary in scope. And yet, the lesson of 3I Atlas warns us that even this grand network will not eliminate uncertainty. Every measurement remains an interpretation. What will matter most is not how powerful our instruments become, but how honest we are in using them. Precision without humility is still blindness. The next stage of astronomy must therefore cultivate not just sharper telescopes, but deeper ethics of attention, an awareness that what we seek in the universe depends on what we are willing to see. Perhaps that's the quiet miracle of observation. It refines not only data, but the observer. Each new instrument doesn't just extend our sight outward, it expands our capacity for patience, for doubt, for wonder. To observe is to practice a kind of meditation, to sit with the universe and wait for it to speak in its own time. And when it does speak, as it did through 3I Atlas, it often says something unexpected. It tells us that mystery is not a flaw in knowledge, but its rhythm. That our instruments, for all their complexity, are still extensions of the same human curiosity that once looked at the stars with naked eyes. And that even the most sophisticated networks of data are, in the end, a form of listening, a collective act of attention offered to the infinite. You know, I suppose that's what defines our place now. We are no longer observers of the universe, we are participants in its unfolding. Every photon we measure changes us a little, deepens our understanding, shapes our next question. 3. Atlas reminded us that discovery is not linear. It's recursive, cyclical, alive. Observation feeds theory, theory refines observation, and the dialogue continues. And so, as we turn toward the future, the next chapter of this story begins to form. The multi-platform methods that reveal the secrets of 3I Atlas will now guide the search for the next interstellar visitor. New observatories will rise, new instruments will awaken, and somewhere out there, another traveler may already be on its way, a fragment of another sun, another history, another question waiting to be asked. The story, then, is not ending, but widening. From the lessons of observation, we move naturally toward what comes next, the roadmap of the future sky, the instruments still being built, and the discoveries that even now are crossing the space between stars, heading silently toward us. If the story of 3I Atlas has taught us anything, it is that the universe is generous with its mysteries, but sparing with its answers. Every discovery seems to open 10 new questions, and every observation, no matter how precise, points to something just beyond our reach. That is the nature of exploration. It moves in spirals, not lines. And so, as we look forward, the task is not merely to interpret what we've already seen, but to prepare for what will come next. The future of interstellar observation is not a single telescope or mission. It is an evolving choreography of instruments, a global symphony of eyes turning outward in quiet coordination. In the coming years, the world's observatories will enter a new era. The Rubin Observatory in Chile, for instance, will begin its legacy survey of space and time, a decade-long effort to map the sky in unprecedented detail. Every few nights it will sweep across the heavens, capturing the faint motion of asteroids, comets, and perhaps, if we are lucky, the next interstellar visitor. Unlike the chance detections of Oumuamua, Borisov, and 3I Atlas, this new generation of sky surveys will not rely on luck alone. It will be systematic, vigilant, almost alive, an automated form of awareness that watches the cosmos in near real time. And yet, detection is only the beginning. The real challenge lies in recognition. Interstellar objects move differently, reflect differently, behave differently from native bodies in our solar system. Their trajectories cut across the familiar geometry of planetary motion like errant notes in a symphony. To spot them early, astronomers must train algorithms to see what the human eye cannot, to notice the odd acceleration, the subtle change in color, the faint irregularities that whisper of origins beyond the sun's gravity. In 2025 and beyond, artificial intelligence will become not just an assistant, but a partner in discovery, filtering torrents of data to find the improbable among the ordinary. Well, perhaps that is the defining trait of this new age, the marriage of human intuition with machine precision. Where once astronomers relied on patience and chance, now they will rely on pattern recognition on scales too vast for a single mind. But that reliance also carries responsibility. Algorithms see only what they are taught to see. If we train them with narrow assumptions, we risk missing the extraordinary because it does not fit the model. So, the next generation of skywatchers must build systems that remain open to surprise machines that, like their makers, can still be astonished. Among these instruments, new space-based telescopes will play a vital role. The Vera C. Rubin Observatory will cover the optical sky, but in orbit, the Nancy Grace Roman Telescope and the James Webb Space Telescope will continue to expand their reach into infrared, where interstellar objects reveal their warmth, their composition, their scars of radiation. These observatories will be complemented by smaller, faster craft like near-Earth surveillance telescopes or deep space probes, each ready to pivot their gaze toward the unexpected. When the next interstellar traveler enters our system, it may be tracked not just by a handful of telescopes, but by an entire planetary network. This networked approach marks a profound shift in the way we see. No longer will astronomy be defined by solitary observatories working in isolation. Instead, it will become an ecology of instruments, ground and orbital, optical and radio, visible and invisible, all speaking to each other in data streams. The next time a faint dot enters the solar system, dozens of observatories will triangulate its position within hours. Spectrographs will analyze its light, polarimeters will probe its texture, radar will trace its shape, and if it's close enough, spacecraft may even be redirected to meet it. Humanity will no longer just observe, it will interact. That is the vision behind the emerging discipline of rapid response astronomy, a model in which discovery triggers instant collaboration. When a new anomaly appears, observatories across the world and beyond can shift in concert, capturing every angle before the moment passes. The speed of communication becomes as critical as the precision of observation. In a universe that moves in millions of kilometers per hour, timing is everything. 3. Atlas reminded us of that. It appeared suddenly, burned briefly across our instruments, and was gone. The next one, we hope, will not escape so easily. But preparation goes beyond telescopes. It involves coordination protocols, standards, shared frameworks of trust. In the past, discoveries of interstellar objects were followed by confusion. Competing claims, data scattered across institutions, delays in verification. To move forward, the scientific community must create clear procedures for confirming and announcing such discoveries. When a new object is spotted, data must flow immediately between teams. Spectral analysis must be prioritized, radar windows secured, observational biases documented. Transparency will be key not only for accuracy but for public trust. The sky belongs to everyone, and every discovery, no matter how technical, ultimately belongs to all of humanity. You know, there's something beautiful about that idea that the next great discovery may not come from a single country, but from a collective consciousness of watchers across the globe. A student in Argentina may notice an anomaly that an algorithm in Japan flags for review. A telescope in orbit may confirm it. Within hours, a community of scientists from dozens of nations could be working together on a single mystery. That is the shape of the future, cooperation born of curiosity. Still, we must also be realistic. The cosmos is vast, and interstellar visitors are rare. It could be years before another appears within reach, and when it does, the window of opportunity may be brief. That's why preparation matters. Even now, engineers and mission planners are discussing concepts for small, agile spacecraft interceptors that can be launched on short notice to chase an incoming object. These probes, equipped with cameras and spectrometers, would rendezvous within days or weeks, capturing data no telescope could match. The European Space Agency and NASA have both begun studying such missions, and China's Tianwen program has expressed similar ambitions. Perhaps, one day soon, a tiny spacecraft will skim the surface of a body born under another star. The idea is breathtaking, to not only observe an interstellar traveler, but to meet it, to touch it, to bring a fragment of it home. Imagine what a sample of such material could reveal: its isotopic ratios, its age, its story of formation. It would be a tangible piece of another solar system, older than ours, carried across the galaxy like a message in a bottle. Such a mission would mark a turning point in science, transforming interstellar astronomy from a discipline of distant observation to one of direct encounter. Yet, as always, ambition must be tempered by humility. The universe has a way of humbling those who rush. To chase an object moving at tens of kilometers per second across the void is no simple task. It requires precision in propulsion, foresight in planning, and luck beyond measure. Even the best prepared missions will face the unknown. But perhaps that is the essence of exploration, to accept risk, not as recklessness, but as reverence. In the meantime, the groundwork continues here on Earth. Data scientists are building libraries of known object behaviors to distinguish the familiar from the strange. Instruments are being recalibrated to reduce false positives. New standards for polarization and spectral measurements are being written to ensure consistency across observatories. Each of these quiet tasks, the checklists, the simulations, the recalibrations, is a form of faith. They are how we prepare for the next whisper from the stars. And when that whisper comes, it will not sound like a revelation. It will begin, as it always does, with a small anomaly, a point of light that moves where it shouldn't. Someone, somewhere, will notice it first, and for a moment, the entire planet will lean forward together, waiting to see what it means. Maybe it will be just another asteroid. Or maybe, just maybe, it will be something that reminds us again of how little we know and how beautiful that ignorance can be. Perhaps that's what makes the roadmap ahead feel so alive. The next decade of astronomy is not about reaching the end of mystery. It's about learning how to live with it gracefully. Every new instrument will sharpen our sight, but it will also deepen our questions. The universe will grow more detailed, not more finished. And in that growing complexity lies a new kind of beauty, the beauty of endless beginnings. Well, if you stand under a clear sky and look long enough, you can almost feel it, the quiet machinery of observation already humming, the great network of telescopes poised like instruments in an orchestra, waiting for the first note. Somewhere, light from another interstellar traveler may already be on its way, crossing the cold between stars, invisible for now, but destined to find our detectors. We are preparing, listening, waiting not for certainty, but for conversation. And as that anticipation builds, a new question begins to emerge, not one of technology or physics, but of meaning. What do these discoveries ask of us as a species? How do we integrate what we learn into the story of who we are? The next step, then, moves beyond science itself, into the realm of philosophy and imagination, into the question of how we live, knowing that we are not alone in motion, but part of a cosmic continuum that stretches far beyond the limits of our understanding.